Top 10 gemstones that were hidden for millions of years. Some have been locked beneath tectonic plates for 500 million years. Others were formed in the seconds after a meteorite hit, then buried under layers of earth that no longer exist. These are not just rare gems. They are records, not of human history, but of geologic time before history, before the continents were stable, before life appeared, before the air we breathe formed, crystals formed in silence. Some carry isotopes older than the moon. Others retain the shape of long-extinct creatures, molecule by molecule. In today's episode, we're not counting gems by price or beauty. We're tracking them through time. These are 10 gems that Earth has kept hidden until now. Rank 10. Red Beryl, formed in silence, found by accident. No tectonic collision, no volcanic cataclysm. Just a controlled anomaly within a silent plateau in western Utah. There, inside topaz-bearing rhyolite, formed over 20 million years ago, a sequence of rare geochemical interactions occurred. Beryllium, among the lightest metallic elements, diffused through silica-rich gas channels. Manganese ions, specifically in the trivalent state, entered the system under exacting thermal thresholds. The result, hexagonal Beryl crystals, tinted red by a substitution mechanism that remains almost chemically sterile elsewhere on Earth. This wasn't a gemstone created by pressure, it was created by constraint. Red Beryl demands conditions so narrow that even minor deviations in temperature, pH, or vapor saturation would dissolve its formation entirely. That makes it not only geologically improbable, but thermodynamically fragile. For decades, the crystals found in the Wawa Mountains were dismissed. Small, deep red, and brittle, they were misclassified as garnet or red tourmaline. Most were opaque. Few exceeded 4 millimeters. It wasn't until mineralogists Maynard Bixby and later John W. Simmons began submitting specimens for structural and spectroscopic analysis that its true identity became clear. Red Beryl stood apart by its chromophore. Manganese 3 plus in octahedral coordination, a rare feature in natural settings. Its pleochroism is subtle, but measurable, crimson to raspberry depending on orientation under polarized light. The Mohs hardness of beryl remains consistent, ranging from 7.5 to 8. But unlike emerald or aquamarine, red beryl doesn't occur in pegmatites or hydrothermal veins. Its formation is rhyolitic, gas phase, and strictly secondary. By the early 2000s, mining operations had narrowed to a handful of least controlled zones, with only one, Ruby Violet Claims, consistently producing gem-quality material. From thousands of kilograms of host rock, less than 1 carat of faceable red beryl might emerge. Even then, the average size remained under 0.5 carat. No new significant deposits have been verified globally. Geochemists studying red beryl consider it a textbook case of volcanic vapor phase mineralization. It appears only in highly oxidized topaz rhyolite that cooled under unusually low pressure gradients. Once the vent field ceased activity, the formation window closed permanently. Current thermodynamic modeling suggests that replicating these conditions synthetically would require sustained precision beyond existing industrial capacity. Red beryl is no longer mined at an industrial scale. Remaining reserves exist in academic collections, geological vaults, and a limited number of closed-loop markets. The U.S. Geological Survey classifies it as a non-renewable low-yield beryllium silicate. It holds no industrial role, no scalable application, and no emerging technological demand. Its relevance is confined to mineralogy, not for how it sparkles, but for how it formed, for what it proves that even in stable crust, under seemingly inert conditions, Earth still creates within margins that escape repetition. Rank 9, Moldavite, impact material in terrestrial context. There was no magmatic chamber beneath it, no mantle plume. Moldavite did not emerge from Earth's internal processes, but from a collision. Roughly 15 million years ago, in what is now southern Germany, a meteorite estimated to be 1.5 kilometers in diameter struck the Earth's surface at a speed of over 20 kilometers per second. The energy released, equivalent to multiple nuclear detonations, did not just vaporize rock, it reassembled it. Moldavite is not a mineral in the conventional sense. It is a form of natural silica glass, a tectite, formed when terrestrial rock was ejected, melted, and cooled in midair. The specific impact event responsible is the Nördlinger Ries crater, now eroded to a 24-kilometer-wide depression. Geological studies confirm the event's date via argon-argon radiometric dating, which indicates that it occurred approximately 14.8 million years ago, during the Miocene epoch. What sets Moldavite apart from other tektites, such as those found in Indochina or Australasia, is its chemical uniformity and transparency. Most tektites are black, opaque, and irregular in shape. Moldavite, however, is green, vitreous, and occasionally gem-grade. This is due to its unique silica-alumina ratio and minimal metallic inclusions, likely a result of its low iron source rock, primarily Upper Jurassic sandstones and shales that were vaporized by the impact. Its formation zone spans the modern-day Czech Republic, Austria, and parts of southern Germany. The strewn field, a technical term for where tektites land, is spread over 300 kilometers, but gem-quality Moldavite has only been consistently recovered from southern Bohemia. Crystals are not extracted from the host rock. They are collected from sediments, where they settled millions of years ago after being thrown dozens of kilometers from the point of impact. Microscopic analysis reveals characteristic flow textures, Larimar inclusions, and vesicular structures, evidence of its rapid cooling and aerodynamic shaping during atmospheric re-entry. No two pieces are exactly alike, and yet all bear unmistakable markers of their violent genesis: swirl patterns, pitting, and the absence of crystalline structure. Moldavite cannot be grown in laboratories in its natural form. Synthetic analogs exist, but they lack the physical indicators of high-energy formation. In controlled settings, even explosive melting of silica fails to replicate the internal structures visible under SEM scans in actual Moldavite specimens. Its classification remains stable: amorphous, tectosilicate-based glass of meteoritic impact origin, not volcanic, not metamorphic, and not sedimentary. The International Mineralogical Association does not define it as a mineral, but it remains of enduring interest to geochemists, planetary scientists, and sedimentary geologists studying extraterrestrial influence on terrestrial strata. In recent years, mining has been restricted due to surface depletion and concerns about illegal excavation. Most legitimate specimens are now sourced from old sediment traps in South Bohemia. The Czech Geological Survey has cataloged over 15,000 individual samples since the 1970s, primarily for use in academic and comparative studies. Moldavite's value lies not in clarity or size, but in origin. It is the only gem-grade tektite known to have formed in Europe, and the only one associated with a precisely studied terrestrial crater. Its provenance is not speculative. Its structure is not anecdotal. It is a glass made by force, documented by physics, chemistry, and stratigraphy. Rank 8, amber, fossilized resin, not mineral. Amber does not crystallize, it does not cleave, refract light along axes, or register on the Mohs scale in the same manner as minerals. Its origin is neither igneous nor metamorphic. It begins as resin, organic, sticky, and alive. Between 30 and 90 million years ago, during the late Cretaceous through early Paleogene, coniferous trees of the family Araucariaceae and their relatives in the now extinct Chirolepidiaceae secreted viscous resin in response to bark damage, unlike sap, which circulates nutrients. Resin functions as a defense, antibacterial, antifungal, and sealing agent. In isolated conditions, such as anaerobic environments in swampy forest floors or sedimentary layers, the resin polymerized, hardened, and resisted decomposition. Over millions of years, it became amber. The fossilization process is not instant. Resin undergoes molecular cross-linking, a process known as diagenesis. Volatile terpenes evaporate. Oxygen contact ceases. Pressure from overburdened sediments compacts the organic material until its chemical identity stabilizes, resulting in the formation of long-chain hydrocarbons. The result is a solid substance with an oxygen content ranging from 8% to 12% by weight, along with trace elements that vary by locality. Amber does not originate from geological heat or tectonic pressure. Its formation reflects preservation, not transformation. This makes it unique among gem materials, an organic fossil that can preserve ancient biological inclusions in exceptional detail. Inclusions of dipteran insects, fern spores, and even dinosaur-era feathers have been documented through advanced microscopy. Some Baltic amber specimens retain complete cellular tissue structure in organisms encased within. Deposits are globally distributed, but not equivalent. The most studied come from the Baltic region, particularly Kaliningrad, in the coastal areas of Poland, where Eocene-age amber forms thick layers of marine sediment. Dominican amber, younger and more transparent, contains a higher rate of biological inclusions due to resin production by Hymenaea protera, an extinct leguminous tree. Burmese amber, among the oldest, dates back to the Cenomanian stage of the Cretaceous period and includes rare finds such as ammonite shells and enantiornithine bird remains. Amber is not rare, but the preservation of pre-tertiary biological matter within it is scientifically irreplaceable. Infrared spectroscopy, gas chromatography, mass spectrometry, and stable isotope analysis have transformed amber into a rich data archive, revealing insights into paleoclimate, plant evolution, and atmospheric oxygen ratios during key extinction events. Commercially, amber has been used since Neolithic times for beads, carvings, and seals. Its role in ritual and trade is extensively documented from Mycenaean Greece to Iron Age China. However, none of that defines its geological classification. The International Mineralogical Association does not consider amber a mineral. It is categorized as an organic gemstone, comparable to jet or coral, with a specific gravity ranging between 1.05 and 1.10. Heat can damage it. Acids dissolve it. It generates static charge when rubbed, a property documented as early as 600 BCE by Thales of Miletus, whose observations contributed to the earliest theories of electricity. But its scientific significance has always come from what it reveals, not what it resists. Amber does not speak of Earth's internal formation. It documents its surface, its forests, insects, atmosphere, and decomposition processes. And in doing so, it preserves a biological chapter that minerals cannot. Rank 7, Jadeite, Myanmar. Collision-formed, mantle-locked silicate. Jadeite belongs to a group of silicate minerals known as pyroxenes, but it does not form under standard crustal conditions. It requires pressure over 10 kilobars and temperatures around 200 to 600 degrees Celsius, conditions rarely achieved except in subduction zones, where oceanic crust is driven deep beneath continental plates. The Jadeite of northern Myanmar originates from one of these zones, forged during the convergence of the Indian and Eurasian tectonic plates approximately 65 million years ago. The region, now known as the Jade Tract, lies in Kachin State near the Uru River. Geological analysis confirms that jadeite formed within high-pressure, low-temperature metamorphic rocks, specifically in serpentinite-derived metasomatic zones. It did not migrate upward via magmatic activity. Instead, it remained confined within shear zones and fault contacts, sealed beneath ultramafic rock for tens of millions of years. Jadeite's distinctive coloration, ranging from near white to deep emerald green, stems from trace chromium content in internal microstructure. However, unlike translucent gems like sapphire or spinel, jadeite's value and classification depend not only on chemistry, but also on grain interlocking, fibrous microtexture, and refractive scattering. It is not cut like most gems. It is carved, often using diamond-tipped rotary tools developed specifically for its mechanical resistance and granular toughness. While nephrite, the calcium-magnesium amphibole variety of jade, occurs in many regions globally, jadeite of gem quality is geographically limited. Myanmar remains the only commercially viable source of supply. Guatemala and Japan produce low-volume material, but none matches the fibrous intergrowth and purity of imperial jade, a term reserved for chromium-rich, translucent jadeite from select Kachin deposits. The presence of jadeite was known locally for centuries, but it was not until the 19th century that it was included in global gemological classification. Scientific classification followed in the 20th century, after X-ray diffraction and electron microprobe analysis confirmed its monoclinic structure and high-density pyroxene lattice. Today, most jadeite-bearing rocks are mined from boulder conglomerates along ancient tectonic fault lines using hydraulic systems or manual excavation. Unlike traditional underground mines, extraction relies on weathering to separate boulders from host rock over time. This exposes jadeite to surface degradation, complicating scientific analysis of pristine specimens. Political instability, environmental degradation, and opaque trade practices have obscured a significant portion of Myanmar's jadeite output in recent decades. While global markets often focus on carving quality or color grading, academic interest remains fixed on its tectonic provenance. The U.S. Geological Survey classifies Myanmar jadeite as a collision-derived metamorphic silicate, distinguishing it from contact metamorphic analogs or metasomatic imitators. Jadeite's chemical formula remains unchanged, but its cultural, political, and economic interpretations have varied across civilizations. From burial relics in the Qing dynasty to offerings in Mesoamerican rituals, jadeite has been used as a symbol, a status symbol, and a form of currency. Yet its geological identity remains constant, a high-pressure artifact of oceanic crust that has been crushed, hydrated, and recrystallized under the Himalayan front. This is not a stone that rose from Earth's interior. It is one that was trapped, caught between slabs of lithosphere, metamorphosed in secrecy, then released only when surface processes exposed the folded remnants of the collision that formed Asia's most incredible mountains. Rank 6, Benitoite, crystallized in subduction, revealed by error. Benitoite's discovery was accidental. In 1907, miners searching for corundum in the serpentine-rich terrain of San Benito County, California, unearthed a blue gemstone unlike anything then cataloged. It was fluorescent under shortwave UV light, fractured differently, and resisted acid etching. Initial assumptions leaned toward sapphire. Mineralogical analysis disagreed. Structurally, benitoite is a barium-titanium silicate with a trigonal crystal system. It forms only under a unique intersection of geologic conditions: low to moderate temperatures, high-pressure bluish facies, and a compositionally rare mixture of barium-rich fluids and titanium-bearing minerals. Such environments exist almost exclusively within subduction zones involving oceanic crust and altered mantle wedge material. California's coast ranges, especially the New Idria serpentinite belt, are remnants of an ancient accretionary prism formed during the subduction of the Farallon Plate beneath the North American Plate in the late Cretaceous to early Paleogene. It is in these convergent margins that benitoite originated, within naturalite veins and cross-cutting fractures in glaucophane schist, often associated with neptunite and wachanite. Geochronological constraints suggest crystallization occurred approximately 100 million years ago, though emplacement into surface-accessible rock likely post-dated that by tens of millions of years. Benitoite's gem-quality crystals are typically small, rarely exceeding 1 carat faceted, and exhibit high dispersion, 0.046, surpassing even diamond. This optical characteristic, coupled with strong pleochroism, blue to colorless, makes it distinct under magnification and spectral analysis. Only one locality on Earth has produced faceable material: the Dallas Gem Mine near Coalinga, California. Although trace findings have been reported in Japan and Arkansas, no other site has produced crystals of comparable size or clarity. The U.S. state of California officially recognized benitoite as its state gem in 1985, not for abundance but for singularity. Mineralogically, it is notable for its incompatibility with synthetic replication. Attempts to grow benitoite in laboratory conditions result in microscopic grains, often twinned and unstable under pressure. Its formation mechanism remains a subject of active research in fluid inclusion thermobarometry and subduction zone geochemistry. Mining ceased in 2006. Today, only surface collections and old stock extractions supply researchers and academic institutions. The mineral's fragile crystal habit, coupled with its geochemical specificity, makes relocation of new deposits unlikely. Modern mapping suggests the tectonic environment that enabled its genesis no longer exists within accessible crust. Benitoite's identification history also shaped mineral classification protocols in the 20th century. It was one of the first gem minerals to be analyzed using X-ray diffraction in the United States. Its anomalous birefringence, high refractive index, and UV fluorescence redefined how gemologists approached unknown bluestones. It shifted analytical practice from gem identification towards structural crystallography. While collectors often focus on its aesthetic properties, academic interest rests in its petrogenesis. Benitoite is a marker of oceanic subduction, captured in mineral form, that records temperature, fluid composition, and tectonic angle within its growth history. This is not a stone of scale, but of precision. It crystallized within a chemical corridor so narrow that it has not been observed to repeat, not because we failed to find it, but because Earth itself no longer offers the setting in which it can grow. Rank 5, Larimar, hydrothermal remnant of a volcanic belt. The material now known as Larimar was identified in 1974, but its geological formation dates back tens of millions of years. Larimar originated within a hydrothermal system associated with an extinct volcanic complex on the Caribbean plate margin. Its structure is a calcium-sodium inosilicate, a variety of pectolite, colored blue by the presence of copper, and in some samples, vanadium. The tectonic setting responsible for its formation was not stable continental crust, but a mobile belt of oceanic arc terrain. The Bahoruco mountain range, where Larimar is found, is composed of heavily altered andesitic volcanic rocks that have been intruded by secondary mineral-bearing fluids. These fluids, enriched with copper ions and silica, move through fractures within basaltic and andesitic host rocks. At low to moderate temperatures, estimated between 100 and 250 degrees Celsius, pectolite crystallized in cavities and veins. In rare cases, copper partially replaced calcium, producing the distinctive blue coloration characteristic of Larimar. Larimar is a product of mineral saturation and cavity cooling. It lacks cleavage, is relatively soft, Mohs 4.5 to 5, and decomposes in hydrochloric acid. Yet its internal structure reveals botryoidal and fibrous crystal habits, sometimes forming radial sprays. Its visual appearance, blue, white, and green banding, is not diagnostic of a single mineral species, but of zoned hydrothermal deposition over time. The only known occurrence of Larimar in significant quantity is in Barahona Province, southwestern Dominican Republic. Early surface samples were misidentified or dismissed as turquoise analogs. It was not until Miguel Mendez and Norman Rilling, a Peace Corps geologist, submitted material for lab analysis that the gem was correctly classified as blue pectolite of volcanic origin. Geological core samples taken in the 1990s confirm that Larimar is not dispersed evenly. It forms in lens-like pods within pillow basalt, which itself is part of a larger ophiolite sequence uplifted by post-Eocene tectonic reactivation. The mining process is artisanal and conducted by hand or with pneumatic tools. There is no host rock exposure at the surface. All material must be located underground, often through vertical shafts following vein structures no wider than 20 centimeters. Larimar has no recorded presence in any other region, despite visual lookalikes in Nevada, Kazakhstan, and Russia. These analogs either lack the pectolite structure, the copper-induced coloration, or the specific volcanic context. As of 2025, its geologic exclusivity is maintained not through trade restrictions, but by geotectonic isolation. Thermogravimetric and Raman spectroscopy studies have confirmed the absence of crystalline water in high-grade Larimar, supporting its formation under relatively dry hydrothermal conditions. These studies also demonstrate that the fibrous lattice responsible for its color cannot be replicated through artificial heat treatment or dyeing, which is one reason it remains a subject of mineralogical interest beyond its ornamental value. Larimar does not represent the deep earth. It is not the product of ancient continental processes or cosmic impact. It is a surface layer hydrothermal anomaly, originating from a now extinct volcanic belt and preserved in an island arc that is now tectonically stable. It belongs to no wider family of commercial stones. Its distribution is narrow. Its classification is precise, and its formation, both chemically and structurally, remains unrepeated in the rest of the Western Hemisphere. Rank 4. Opalized fossils. Replacement without recrystallization. Opalized fossils are not found in sedimentary layers by chance. They are the result of a precise geochemical sequence that enables one material to substitute another without altering the shape, volume, or fine structure of the original organism. The process is called permineralization via silica gel infiltration, and under rare conditions, it produces hydrated silica, commonly known as opal, which is chemically represented as SiO2.NH2O. Most known specimens originate from the Great Artesian Basin in Australia, a sedimentary basin covering over 1.7 million square kilometers. During the Cretaceous period, approximately 100 million years ago, this region was a shallow inland sea. Marine reptiles, mollusks, and plant material were buried in calcareous silt. Over time, acidic groundwater leached silica from volcanic ash in overlying layers. The silica, transported in solution, infiltrated the voids left by decaying tissue. Unlike quartz, which recrystallizes under high pressure and temperature, opal forms at low temperatures, typically under 45 degrees Celsius. The gel-like solution gradually hardened, filling bone structures, shell imprints, and even delicate root cavities. No external mold was used. The fossil became the host and the substrate. In the best cases, the opal preserves both the macro and microstructure of the original life form. Most opalized fossils are composed of common opal, also known as potch. However, rare specimens display a play of color effect due to internal diffraction caused by uniform silica spheres. These are classified as precious opalized fossils and may include vertebrae, bivalves, or even sections of dinosaur bone. Not all opals with fossil patterns are fossils, and not all fossils with opal content are diagnostic. Accurate classification requires thin sectioning and scanning electron microscopy. Australian regulations require the registration of all significant fossil opals that exceed a scientific threshold. The Lightning Ridge and Coober Pedy regions have yielded the majority of known specimens. One of the most studied, Wearosaurus pabini, a small Cretaceous ornithopod, was identified entirely through opalized cranial fragments. CT scanning and laser ablation isotope analysis revealed not only species traits but also post-mortem mineralization pathways. Elsewhere, opalized fossils have been found in Ethiopia and parts of the U.S., but these lack consistent coloration and microstructural fidelity. Their formation environments are not marine but fluvial, and their geologic stability has not been established. The Australian examples remain the standard for comparative paleosilica research. From a petrological standpoint, the transformation from bone to opal is not considered a phase transition. There is no change in atomic structure through heat or pressure. Instead, the fossil is chemically replaced, molecule by molecule, in an aqueous system, while the geometry remains intact. This makes opalized fossils a case of pseudomorphic preservation, not recrystallization. They are not stones shaped by force or crystallized by heat. They are biological records suspended in amorphous silica, stable, hydrated, and optically active. Their scientific value exceeds ornamental use, and their retrieval is monitored under multiple layers of paleontological regulation. As of 2025, the Australian Opal Centre maintains the world's most complete registry of opalized fossils. Each specimen is documented with mineralogical, biological, and geochronological data, ensuring that none are removed without full academic traceability. These are not remnants of mineral formation. They are remnants of life, mapped onto a non-crystalline lattice that carries no cleavage, yet retains its whole structure. Rank 3. Grandidierite, orthorhombic mineral from anatectic metamorphism. Grandidierite was first described in 1902 by Alfred Lacroix, following the collection of pale green crystals by field geologist Alfred Grandidier near the cliffs of southern Madagascar. But identification did not equate to understanding. For decades, its structural properties were difficult to resolve, and its natural context remained ambiguous. Only with the advancement of geothermal barometry and mineral inclusion studies in the 21st century did its origin begin to clarify. It crystallizes in the orthorhombic system and exhibits pleochroism, shifting between green, blue-green, and yellow-green depending on orientation. What distinguishes it from other silicate minerals is not merely color, but its genesis within high-grade metamorphic assemblages. Specifically, it is a product of anatexis, the partial melting of crustal rocks under intense pressure and temperature during granulite facies metamorphism. In southern Madagascar, the host rocks are Neoproterozoic gneisses and aluminous metasediments that were metamorphosed during the Pan-African orogeny approximately 550 million years ago. Under pressures exceeding 6 kilobars and temperatures above 700 degrees Celsius, boron-rich fluids reacted with magnesium and aluminum-bearing minerals in situ. The result was Grandidierite, recrystallized in foliation parallel veins and intergrowths with other borosilicates like dumortierite. Field relationships indicate that Grandidierite does not form in intrusive pegmatites, hydrothermal veins, or contact orals. It is instead a product of deep crustal evolution, confined to narrow structural zones where the mineral chemistry aligns precisely with the fluid composition. These occurrences are neither abundant nor randomly distributed. As of 2025, fewer than 5 global deposits have produced Grandidierite with a traceable primary origin. Its rarity is not the result of depletion, but of paragenesis. In Madagascar, Grandidierite appears in amphibolite grade units near Tranamaro and Anosi. Outside this region, documented occurrences exist in Sri Lanka, Malawi, and Norway, though gem-quality specimens remain almost entirely limited to southern Madagascar. Many reported samples from elsewhere were later confirmed as holtite or bluish-green tourmaline through Raman and XRD analysis. From a crystallographic standpoint, Grandidierite presents a biaxial optic system with high birefringence and a refractive index range of 1.590 to 1.623. These features, alongside its hardness of 7.5 and resistance to cleavage, render it durable yet rugged, prone to facet due to internal stress zones and directional inclusions. Most gemological interest lies in thin section analysis and inclusion mapping, which reveal its growth sequence and post-crystallization deformation. The mineral's classification is stable under the Struens and Dana systems. It is not subject to redefinition, and its status as a type locality species remains academically fixed. No synthetic analogs have been confirmed, nor has any attempt at commercial synthesis produced a structurally valid match under controlled lab conditions. Grandidierite does not trace a biological past. It carries no fossil record. It has no association with sedimentary cycles or volcanic eruptions. It is a residue of continental reconfiguration, formed not in fluid cavities but within the deeper architecture of crustal plates undergoing partial melting and deformation. As such, it represents a static mineralogical endpoint, a compound that only stabilizes when metamorphic energy approaches exhaustion. Rank 2, Tanzanite, recrystallized zoisite along a rift margin. Tanzanite is not a mineral species. It is a variety of zoisite whose violet-blue hue arises only when trace amounts of vanadium substitute for aluminum during crystal growth. The material itself was not geologically recent, but its emergence as a distinct gemstone occurred less than 60 years ago, triggered not by tectonic uplift, but by a lightning strike that exposed surface veins in northern Tanzania's Miralani Hills in 1967. The region lies within the Mozambique Belt, a Proterozoic mobile zone shaped by multiple orogenic phases. Tanzanite-bearing zoisite is found in graphite garnet gneiss complexes subjected to amphibolite facies metamorphism, typically at pressures between 5 and 8 kilobars and temperatures exceeding 600 degrees Celsius. The vanadium source remains debated. Some attribute it to metasomatic fluid infiltration, while others attribute it to local sediment-derived protoliths with elevated V2O5 content. What is geologically unique about Tanzanite is its formation environment, a narrow corridor of high-grade metamorphism adjacent to the East African Rift System, where extensional forces reactivated ancient shear zones. Zoisite crystallized in laterally continuous, centimeter-thick veins, frequently oriented subparallel to foliation. These veins underwent subsequent deformation, resulting in twinning, zoning, and internal strain features that are detectable via X-ray topography and polarizing microscopy. The distinct coloration for which Tanzanite is known does not exist in its natural state. Crystals are brown to reddish-brown when extracted. The blue-violet appearance is the result of controlled heating between 400 degrees Celsius and 600 degrees Celsius, a process that oxidizes vanadium from V3+ to V4+, altering absorption bands in the visible spectrum. This treatment is permanent, irreversible, and stable under normal environmental conditions. From a crystallographic standpoint, Tanzanite is biaxial positive with strong pleochroism, appearing blue, violet, or burgundy depending on viewing angle. It exhibits perfect cleavage in one direction, rendering it mechanically vulnerable during the fast-sitting process. Most faceted stones are oriented to maximize the blue axis, though this sacrifices yield and increases loss due to cleavage planes. The Miralani deposit is the only known source of gem-quality Tanzanite. Similar zoisite has been reported in Pakistan and Kenya, but without comparable saturation, clarity, or vanadium concentration. As of 2025, no additional commercial deposits have been discovered globally, and extraction is tightly regulated through Tanzanian government licensure. In gemological literature, Tanzanite is classified as a heated variety of orthorhombic zoisite. It is not a separate species, nor a mineral group. Its distinction lies in the activation of trace elements under high-pressure crustal conditions, followed by post-extraction treatment, placing it at the intersection of geology and human-controlled enhancement. The mineral's presence within a rift margin and its confinement to a single, approximately 7-kilometer-long mining belt reflect its sensitivity to geotectonic microstructure. Without the specific interplay of metamorphic grade, fluid chemistry, and shear zone geometry, Tanzanite-grade zoisite does not form. Its scarcity is not just a function of mining output, but also a result of petrogenetic improbability. Tanzanite is not ancient in use, but it is ancient in origin. The rock units that host it predate the Cambrian. The blue that defines it was never visible until the 20th century, and the conditions that produced it may never converge again along any other plate boundary. In first place, zircon crystals that record Earth before life. Zircon is not a traditional gemstone. It is a geochronometer, a compound that holds in its lattice the age, temperature, and isotopic identity of Earth before the emergence of stable continents, before oxygen, oceans, or known life forms. The oldest zircon ever measured was extracted from metamorphosed sedimentary rocks in the Jack Hills region of Western Australia. Radiometric dating, specifically uranium-lead decay, places it at 4.4 billion years, only 160 million years after Earth's formation. This date does not reflect the age of the host rock. It reflects the crystallization of the zircon grain itself, preserved through multiple cycles of burial, metamorphism, and tectonic transport. Zircon forms in igneous melts that are rich in silica and contain incompatible elements. As magma cools, elements such as uranium, thorium, and rare earths preferentially enter the zircon crystal lattice, but lead, its radiogenic decay product, does not. This makes each zircon grain a self-contained radioactive clock, immune to many later geochemical alterations. Unlike feldspar or quartz, zircon resists dissolution, mechanical breakdown, and thermal resetting. Its melting point exceeds 2,200 degrees Celsius. Its survival across multiple orogenic cycles is not an anomaly. It is a property. Zircons from Jack Hills are not gem quality. Most are below 300 microns in length, but under secondary ion mass spectrometry, they reveal isotopic signatures suggesting surface water was present on Earth over 4 billion years ago. Others preserve inclusions interpreted as quartz, muscovite, or even possibly carbon, though such interpretations remain contested. The Hadean Eon, the first 500 million years of Earth's history, lacks a coherent rock record. Zircons are the exception. They are not remnants of a single event, but a recurring mineral phase that formed, recrystallized, and redeposited through crustal recycling. A single grain may contain growth zones dated hundreds of millions of years apart. Laser ablation across those zones reconstructs partial histories of crustal differentiation that occurred long before the emergence of stable continental lithosphere. Beyond Jack Hill's, detrital zircons of Paleoproterozoic and Archean age have been found on all continents. They are used to track the assembly of supercontinents, the onset of plate tectonics, and the shift from primordial crust to modern-style subduction. Their internal zoning, trace element chemistry, and fission track patterns are the foundation of modern zirconology, a discipline that operates at the boundary between petrology and time. Gem-quality zircon, transparent, blue, heat-treated, is a different material in application, though not in structure. It lacks the isotopic integrity of detrital grains used in geochronology, having been recrystallized or modified during metamictization. In geological laboratories, such specimens are discarded, not for impurity, but for instability. In planetary science, zircon is more than a mineral. It is a calibration tool for other worlds. Lunar zircons retrieved from Apollo missions have clarified the moon's cooling history. Martian meteorites containing zircon fragments provide lower bounds for the stabilization of the Martian crust. Zircon does not exist to be seen, it exists to be measured, to be read. Each grain is a closed archive, not of what Earth became, but of what it once was, when no rock remained stable and no memory could last except this. What these gemstones reveal isn't just how minerals form, but how time accumulates. They are not prized because they sparkle. They are studied because they endure. Through impact, heat, burial, and tectonic collapse, these materials preserve structures, compositions, and isotopes that outlived oceans, outlived species, and outlived continents. Each one marks a chapter Earth didn't intend to share. However, by cutting, polishing, and placing them under microscopes, we still read them anyway. To understand a gem is to read a fragment of Earth's memory. Let us know which one resonates with you in the comments, and don't forget to like and subscribe to our channel for more content like this.